I'm pleased to welcome Joseph Cotruvo to the podcast. He is the president of Joseph Cotruvo and Associates, Water, Environment and Public Health Consultants, where he provides advice to various groups, including the World Health Organization's guidelines for drinking water quality and numerous oversight panels on drinking water quality issues, desalination, and recycled potable water reuse, among many topics. He was the first director of EPA's Drinking Water Standards Division after passage of the Safe Drinking Water Act, and director of the Risk Assessment Division in the Chemical Toxics Program. So thank you so much, Joe, for joining me today. We're going to focus our discussion today on the recent PFAS regulations and how they have evolved over the past few years, and what it means for water systems in the US. From there, we will discuss the general process of developing contaminant regulations for drinking water. So thanks a lot, Joe. You've done quite a bit of work on PFAS, and your publication in Groundwater the last year is highly cited. And so maybe you can start off telling us what PFAS is and why these chemicals are important. Did you hear me?
Hey.
Yeah.
Thank you, Bridget. Nice to be with you. I hope you find this to be informative, and you may find it to be a little bit different from what you read in the press, because I'll be digging into details that frequently are overlooked, sometimes by the press, sometimes by EPA too. So, but it's all factual. And the data are available to you, and there are slides available that summarize much of it. So happy to be with you, and let's start off talking about what is PFAS. Well, PFAS is really the simple acronym for several thousand of potential commercial chemicals and byproducts of those chemicals. The one everybody knows is Teflon, of course, which is polytetrafluoroethylene. It's a polymer, and widely used in coatings of cooking utensils. However, has many, many important industrial applications because of its very lubricious, it's very inert. And that's kind of a general characteristic of many PFAS chemicals. PFAS means perfluoro
alkyl. Perfluoroalkyl substances.
Right. Now, there are thousands, perhaps hundreds commercial, but the rest of them are sort of byproducts that probably were produced during manufacture and probably, in many cases, got dumped into rivers or groundwaters. The two most prominent ones, and by the way, what they are chemicals where the carbon-hydrogen bond in the chemical was converted into a carbon-fluorine bond. And so the common name for something like perfluorooctanoic acid is PFOS, or PFOA, perfluorooctanoic acid. And so all of the carbons have no hydrogens attached to them, fluoride only, and it's an acid. Now, what does the fluorine do? Well, these are very interesting chemicals because they're kind of super detergents in a sense. The carbon fluorine end of the molecule is very hydrophobic, means it repels water. It doesn't pick up any water. On the end of the molecule is a acid, carboxylic acid. Acids are ionic. They tend to dissolve. So you have a chemical which on the one end is very polar and capable of dissolving in water. On the other end is very nonpolar and very good at picking up oils and dirts and things like that. So that's PFOA. PFOS is the other one that is very prominent and regulated by EPA now, and that's fluorooctane sulfonic acid. Now, sulfonic acid means it's related to sulfuric acid. So it's a very strong acid. And the presence of the fluorine carbon bonds actually makes it a stronger acid. It's not stronger than sulfuric acid, but it's a much stronger acid than just octanoic acid. So, and that's because of the fluorine is electronegative. It withdraws electrons, so it stabilizes the anion. Now, there are, as I said, hundreds, thousands of others, amides, or ethers, a whole variety of chemical structures that were designed for specific purposes.
That's well, we see a lot about it in the newspaper these days, and so people are asking a lot of questions about PFAS. So it's good that you can explain it to us. So as you mentioned, per and polyfluoralkyl substances, PFAS, and there are thousands of these chemicals. And we've used them in many different substances. And you mentioned, they're water repellent. They're used for non-stick substances and for water repellency. So you mentioned Teflon cooking ware, and also people's rain gear or water vortex material, and firefighting foams. And they've been produced since the 40s and 50s. So we've had them around for a long time. So it's only in the last couple of decades that we've become concerned about their environmental impacts. So this year in 2024, EPA came out with new regulations related to PFAS. And these regulations have been evolving over the past few years. And so maybe you can describe what the regulations that were passed in March this year, what the maximum contaminant levels were, and how that has evolved over time.
Okay, I should add one more thing about description, and that is that because of these carbon fluorine bonds, these substances are extremely stable. They're not metabolized by bacteria. They're not hydrolyzed. And so they have very long lives. And the common press name is Forever Chemicals, which actually isn't too far from the truth, surprisingly. And forget another factor that's important is they're also not readily metabolized when you ingest them. And so they have relatively long half-lives in the blood. So, for example, for the PFOA and the PFOS, people argue about what the half-life is, but it's probably a couple of years in the blood. Some of the other lower molecular weight chemicals, like the C4, rather than the C8, which is the octanoic, the C4, the butanoic, probably has a half-life in the blood of about a month. And so for that reason, it's considered to be much less toxic than the C8s. And in fact, I think most of the toxicity, these are not particularly toxic chemicals, but most of the toxicity is because once ingested, the effective dose is much greater than what the concentration in the food or the water indicates, because it doesn't go away. It accumulates in the blood. And so let's say if it's impacting the kidney is not releasing it. And so it just keeps, it stays in the blood. Mm-hmm. And perhaps that's one of the mechanisms where there could be some kidney toxicity as a result. So anyway, they're quite unusual. They have unique properties, and but they're mostly very, very useful, very effective substances. Now, I'd say one more thing. Teflon, which got a lot of bad press about 10 years ago, actually is a negligible source, because Teflon, first of all, the polymer is not what we're concerned about. The polymer is there on the pan. However, the way they manufacture the polymer is they polymerize tetrafluoroethylene in water emulsion. And the emulsifier that's used is PFOA. And so the polymer forms, it precipitates, they filter it off. A little bit of PFOA probably is entrained in the polymer that's left. However, they then put that dried polymer on the pan, heat it up to about 700 degrees. And so if there's any PFOA left, it's going to volatilize because the boiling point is less than 200 or so. So the point is, Teflon got a lot of bad press, probably all wrong, but this is America.
Yeah. It's difficult to make sense out of these things when you don't know all the details,
Yes.
So you read
Yes.
the newspaper or whatever, the news, and then you cannot figure out what the risks are. So EPA released the maximum contaminant levels this year in March. And so maybe you can describe those levels and also the history behind developing those levels.
Okay. Well, maximum contaminant levels for contaminants in drinking water are produced under the Safe Drinking Water Act. And there are hundreds of substances that are regulated under the Safe Drinking Water Act, either individually or as in groups. The maximum contaminant level is related to something else called the maximum contaminant level goal. The goal is defined in the law as the level of a substance in water that would result in no known or anticipated adverse effect on health with a margin of safety. So the goal is the ideal level of negligible risk. The MCL, the maximum contaminant level, is defined in the law as the concentration in drinking water that is as close to the maximum contaminant level goal as is technically and economically feasible, taking cost and other factors into consideration. So these are important definitions because they determine what those numbers can be. Now, in the case of PFAS, PFOA and PFOS, the goal levels were 0. Now, what does that mean? Well, it means that the ideal is that there wouldn't be any in the water, which we would all agree philosophically. But that's, of course, unattainable because, if you can measure parts per trillion or parts per quadrillion or whatever, you can always find a few molecules of everything everywhere. So the point is, EPA then wrote regulations at 4 parts per trillion for PFAS, PFOA, and 20 parts per trillion for PFO.
No, I think it's 4 for both.
Is it 4 for both?
Yeah, 4 parts per trillion for PFOA and PFOS, and 10 parts per trillion for others.
Sorry. Yes, you're right.
Yeah.
You're right. Thank you.
Yeah.
Now, the reason they chose 4 is because the law requires that the substance be analyzed. You need to be capable of analyzing it. And 4 parts per trillion is the level that has been currently determined by comparative laboratory studies as to be the lowest level that is correct. In other words, capable of being reproduced and capable of being analyzed in commercial laboratories or in laboratories. And that would be the reporting level. Now, analytical methods can usually detect a little lower, but they're not really reliable numbers when they're below the MRL, the reporting level. So 4 is the reporting level. So that's why they chose 4 as the MCL for PFOA and PFOS. They chose 10 for several other similar chemicals, and those chemicals, however, are present in much, much, much lower prevalence. But they decided to regulate those two individually. But then also they created a hazard index idea, which is if you basically add up the concentrations of the chemicals that you would find in a sample, and then you divide that by a certain toxicology value for each one. And if that number comes out greater than 1, then that's a compliance issue. You're supposed to get below that. It's a kind of a convenient thing to do. Unfortunately, it's scientifically untenable because the toxicology of each of them is different. And they don't necessarily interact with each other. So having a mixture of them doesn't necessarily mean that you reach a number that exceeds a health-based number. It's a number. That's all. And so in other words, it assumes that there's some kind of toxicologic interaction or additivity, but they probably affect different organs in different ways at different potencies, and therefore it's rather scientifically untenable to do that.
Right. And you mentioned earlier, Joe, that octanoic acid with 8 carbons and with a half-life in the bloodstream of, maybe a few years. And so it can bioaccumulate and then have higher toxicity. But if you only had 4 carbons, or if you had shorter chain compounds, they would have, much shorter half-life in the bloodstream and then would be much less toxic. But are they as effective as the longer chain compounds? Could we replace the longer chain compounds with the shorter chain compounds and have the similar effects in terms of non-stick, water repellency, and all those other things?
I think, each substance has its own efficacy for some end use. I would assume that since the most common chemicals were the C8 chemicals used for dirt repellency and so forth, and for foaming and such, I would assume that they're more effective for that application than the C4s. However, interestingly, PFOS was the principal component in Scotchgard. And Scotchgard was put on everything: carpets, furniture, clothes, Gore-Tex coats, fabrics, everything. And as a result of that, there was quite a lot of human exposure from inhalation and dust and so forth. The good news, by the way, is that's been stopped about 20 years ago. And so now the blood levels of PFOS are about 90% lower than they were back in 2000. However, the replacement, as I understand it, is the C4, the butane sulfonic acid, perfluorobutane sulfonic acid, which may or may not be as effective. It's going to be more volatile for sure, since it's a smaller molecule, but it's still an acid, so it's somewhat suppressed. Nevertheless, as I understand it, that's the substitute, and for other similar applications. And the reason it's being used as a substitute is because it's apparently significantly less toxic potential.
Right. Yeah. So, the US and the EPA came out with the MCLs in March this year. So a lot of other countries and the World Health Organization have been working on developing PFAS regulations also. So can you describe what these other countries are coming up with, like Canada, Europe, Australia, and the World Health Organization? What levels they're suggesting?
Many of them are very different. The US values are the lowest that I found around the world. And what that means is that there's really no real international consensus on the toxicology of these chemicals. There are different opinions, points of view, august advisory committees coming up with different numbers, which makes you wonder. And by the way, the numbers are very different in many cases, because if you're talking, let's say in Europe, the typical number for drinking water is 100 parts per trillion. The US number is 4 parts per trillion. So that's a factor of 25, which is quite unusual when one is looking at chemical toxicity values. If you looked at the health advisory, which is 4 parts per quadrillion, 0.004 ppt, that's 25,000 times different. So, unfortunately, there's a lot of controversy, a lot of uncertainty, and many different opinions as to what are what you would call safe levels of exposure to these substances. My position all along is what we need is an international consensus. These chemicals are present everywhere in the world. They're manufactured mostly in China these days because many were stopped in the US and Europe. They get into the rain. They're found in rain. They drift across continents. They're used in all kinds of products. It's an international situation. It should be solved internationally rather than individual countries picking numbers.
Right. Yeah. And the range that you mentioned for the different countries reflects the uncertainty in the toxicity, I guess.
Yes.
When you mentioned, I think the World Health Organization originally put out 100 parts per trillion PPT for PFOA and PFOS.
Yes.
And 500 PPT for total PFAS in 2022. But then now they are still evaluating those levels.
Yes, they received a tremendous numbers of organized negative comments, and it was a write-in campaign by certain groups. And they, I guess, were intimidated by that and decided to withdraw that draft, which was out for comment. And they've now empaneled another committee to produce another value. And it will probably take quite many months for them to do that. And then once they have a proposed value, there will be internal reviews, external reviews, comments, revisions, et cetera, et cetera. So it's going to be, I would guess, 1 to 2 years before we see a new WHO number.
And you also mentioned Canada has 30 parts PPT for total PFAS, including, yes, I think, like 25 different substances, PFAS substances. So
they took, they looked at this picture and they said, gee, there are lots of potential PFAS chemicals around. How are we going to be able to produce individual numbers for each one? Every time somebody finds one in the water, that somebody's going to want a number. And so they said, really, as a kind of a common sense approach, they said, instead of individual numbers, we're just going to say 30 parts per trillion in the drinking water total, as you mentioned, as measurable by the current analytic techniques, which is about 25 individual substances which have been validated that way. There aren't really 25 of them in the water. And if there are, they're in very, very unique locations. But nevertheless, that really saves them a lot of work it provides specific guidance for the water suppliers. If you're going to exceed this, put in the technologies rather than going, well, today we had 4 parts per trillion of PFOS, and tomorrow we had 3 parts per trillion of PFOS. What should we do? It's a reasonable, practical approach from a regulatory agency. And by the way, in Canada, relatively small impact because they don't have very many locations with high amounts. Apparently, they didn't manufacture them in Canada, so they can do it.
And you mentioned Europe, the European Union, 500 PPT for all PFAS, and that was the European Chemicals Agency. That was a directive from 2021. So that seems to be much less stringent than what the US has put forward.
I'm assuming that they'll reevaluate it and someday come in with a lower number. More data keeps accumulating, although the data is, as far as I can tell, is not really definitive. And I think the WHO description was there are contradictions between the various studies that have been published. Hundreds of studies, by the way, not 1 or 2. Contradictions, inconsistencies. Therefore, WHO took a kind of a practical approach. They said, well, 100. It's achievable. It gives you a reasonable distinction between those that have a lot and those that have a little, and is a practical way to deal with it. They did not say it was a toxicology-based number, other than it was probably acceptable. And as I say, this write-in campaign was, I think, by a bunch of toxicologists who argued, well, the number should be much, 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 much lower. And so the rest is history.
And Australia has also been fairly active looking at PFAS issues. And I think they proposed 100 PPT and also questioned some of the toxicology studies related to PFAS in Australia.
Well, Australia, actually, interestingly, just a couple of days ago, Australia issued draft revised guidelines for external review. And now remember, Australia does guidelines. Australia doesn't do standards. And so the national guidelines are then available to the individual provinces to decide what to do. Now, typically they will adopt them, but they're not obligated to by law. So it's a very different situation than in the United States. Or in the United States, national regulations apply to everybody. And the states are not allowed to pick a higher number. They can pick a lower number, and some do. But one could argue, well, there are different circumstances in different states, and so they might want to pick a lower number for a higher price. Of course, it costs more because you have more noncompliance. So they have that option.
Right. And so, when I was looking at these issues, originally the EPA had a health advisory of 70 PPT, and then they reduced that to 0.004. So they really have changed quite a lot over time. And then one of the things I was looking at was the relative source contribution from water. So drinking water, in the interim health advisories for these PFAS compounds, the relative source contribution from drinking water is estimated to be 20%, account for 20% of the exposure, and 80% from all other different sources, like you mentioned, Scotchgard, carpets, all of these other things.
That's right. Now, it's pretty clear that in almost all cases, the other sources are much greater than drinking water. And that means diet and maybe a little from inhalation, but certainly seafoods, fish, even some vegetables and such, have ultimately lead to greater intakes of PFAS than almost all drinking waters, except for some of those drinking water locations that we mentioned were near sources where the groundwater was contaminated. Now, by the way, in that situation, once the groundwater is contaminated, it may take 100 years for it to flush out. On the other hand, as far as most of the large public water systems where most of the population exists are using surface waters, rivers. They flush out very quickly. And so in reality, the exposures from most surface waters are going to be much, much less than the exposures from some of those groundwaters. Now, the problem is that the regulations apply universally. So everybody has to monitor continually. Perhaps it depends, but let's say 4 times a year. And you have to monitor, analyze at every entry point into the distribution system. So the samples cost about $300 a piece. So even if you don't have PFAS in the water, you still have to monitor and you have to pay the $300 per sample. And in some cases, it could be 100 samples a year, depending on the specific location. So now, by the way, back to relative source contribution. The relative source contribution number is an arbitrary number. It's, in this case, it's not based on some measurement that somebody did. It's what it is, by the way, it's kind of misleading because what it says is we are going to allow drinking water based on our calculations to contribute not more than 20% of the total daily exposure. But what that really does, it places a much greater burden on drinking water rather than the people who are the greater sources of exposure. So if they said the relative source contribution from drinking water is 80%, the number would be 4 times higher. Instead of 20% to 80%, it's a factor of 4. So in other words, that relative source contribution is not really well understood by many people.
Well, that seems counterintuitive to me. So I didn't understand it. So thank you for explaining that. But then you also mentioned, food as a source.
Yes.
And, shellfish and I have heard of yogurts and other types of food. So then I'm wondering, what is the FDA, Food and Drug Administration, doing about PFAS in food?
That's a very good question, because not only can PFAS be present in the product, in the vegetable, let's say, or the fish, but it can also be present in the packaging. And so, and of course, FDA has control over packaging. They can determine what's acceptable and what's not acceptable. As of today, as far as I know, they really have not concluded that there's a significant concern from the presence in the American diet, which is interesting because, you have 2 agencies who are in the same city and work for the same government, and they seem to have very different conclusions. Now, one argument you could say is, well, you can regulate drinking water more easily than you can regulate food. Not food packaging, but we're saying food. And therefore, it's more feasible for the government to regulate drinking water rather than some of those food products. On the other hand, it poses a significant economic burden to the general public because the general public pays for the drinking water that they consume.
Right. Yeah. And I guess, that leads to the linkages between PFAS in water and PFAS in food and also wastewater. So
Yes.
when you land apply sludge and stuff, sometimes it can have high PFAS levels. And then the food or the dairy products that are generated there could have high PFAS levels. But I think they're identifying those, and so managing those hotspots.
It's kind of the law of unanticipated consequences, which always exists. You make a decision and there's a downside issue. And in the case of wastewater, well, where does the wastewater get its composition? Well, from people who are shedding it, who have inhaled it or consumed water or consumed food. So that gets into the waste stream. At the wastewater treatment plant, they're not really designed to remove this kind of chemical, but there is some removal that occurs in the sludge, particularly. And so when that wastewater is treated and the sludge is separated, a portion is removed. A lot of it is concentrated in the sludge. The sludge now is, in many cases, used as agriculture soil treatment and as fertilizer and soil amendment commercially, because it's got a lot of nutrients in it. And so it's really, for the sake of recycling and waste reduction, it's a great idea. On the other hand, nobody assumed that this could be a problem until fairly recently. And as a result now, food that dairy cattle eat, vegetables, and many others have picked up some of these substances from the soil, and that's carried to the consumer. It's a difficult one to deal with.
Right. And also EPA indicated that PFAS compounds are also designated as hazardous waste.
Yes.
According to the Superfund regulations in April this year. So that will make it, if you treat the water to remove the PFAS, then you're going to be generating a hazardous waste.
Yeah, that has broader consequences. For example, anybody that's using this material in a process or manufacturing it, in order to discharge it, they have to meet certain requirements. There are, under the Clean Water Act, for example, there are NPDES permits that everybody has to meet, National Pollution Elimination Discharge permits. And so every facility that uses, manufactures, discharges, including wastewater treatment plants, are subject to NPDES permits. And so listing it as a hazardous waste then is a consequence in terms of what will be the NPDES permits that are calculated locally. So it's part of a large matrix of issues that have to do with trying to reduce exposures to PFAS and reducing entry into the environment.
Right. And we've talked a lot about, the different types where PFAS is found, like nonstick pans, carpets and clothing and all of these different things, Scotchgard. And then you mentioned that groundwater aquifers are a more important source than surface water. Unfortunately, our large public water systems, most of them rely on surface water.
Yes.
And so that's a good thing. So then it's small water systems oftentimes relying on groundwater. But the highest concentrations will be found next to where they were manufacturing PFAS, or next to military bases where they were using it. Maybe you can describe that a little bit, the military bases and what Department of Defense is doing related to PFAS.
And airports.
And
too.
airports.
And by the way, there's a perfect analogy to volatile synthetic organic chemicals, VOCs, trichloroethylene, tetrachloroethylene. We were dealing with the same issues in the 1970s when water was being analyzed. Some of those organic solvents were being detected. Again, frequently near military bases and such in that case where they were used for cleaning parts and equipment and spilling into the ground and percolating into the groundwater. So it's a rather similar situation.
Right. And then you mentioned that they selected 4 PPT because that was the minimum reporting level that was achievable with the techniques that are used to analyze for PFAS. So they need to, I'm wondering how many labs there are in the US that are accredited to measure PFAS compounds.
I don't know. There are a number of major commercial labs we know in the U.S. This is a bonanza for them, of course, because there are 50,000 community water systems. There are 150,000 public water systems total. That all of the community water systems have to do something, and some of the others do. And so multiply 50,000, let's say, times 10 samples a year, let's say, just to pick a low number. That's a lot of samples. And multiply that by EPA's estimate, $300 per sample. It's a bonanza. Now, some water suppliers could do their own analyses, but it's a very sophisticated analysis. To get down to parts per trillion takes very carefully designed facilities and protections against cross-contamination and atmospheric deposition from the air in the lab and absorbance onto the glassware and all those kinds of things. It's a really tough one. So I think most people will go commercial.
Right.
Now, by the way, the good news that I don't know if I mentioned it before, but the good news is that the actual blood levels of PFOS and PFOA are now about 90% less than they were 20 years ago, 25 years ago. So, in other words, it was a much bigger issue back then than it is now in terms of human exposure from water. So EPA had to make a decision on regulation. Now, everybody agrees that they should be regulated. No question. They should be regulated because of their physical chemical properties. The issue is, of course, what's the right number? What's the number that should be chosen that will be safe, but at the same time be not unreasonable relative economic impact? EPA's calculations of benefits from the regulation estimate $1.5 billion of benefits per year in illnesses avoided, cases avoided. That's, you calculate benefits. You say, well, if it's kidney disease, the cost of treating a kidney disease patient is X dollars. You do an estimate from there. Their calculation of the costs, after many iterations, ultimately turned out to be $1.5 billion also. And so, in other words, even under their calculations, it's a break even in terms of cost and benefits. Now, AWWA has done its own cost analysis, and they come out to about $3 billion of cost per year for putting in treatment and the analysis and all that sort of thing. So there's considerable disagreement on that aspect of it, the cost-benefit balance. And as AWWA argues that there are a number of significant consequences of concern relating to costs to water supplies. And what they would argue, more significant concerns and risks than these at 4 parts per trillion. Now, at 10 parts per trillion, there would be much, much lower impact economically. And so the number that you pick, it has a significant impact on the costs as well as potentially on the benefits.
Right. And these water systems have until 2029 to come into compliance. And so they've been monitoring levels in water systems, UCMR data, unregulated contaminant monitoring rule data to evaluate the levels and stuff. And so they're collecting a lot of those data in the US. And the Environmental Working Group is putting out maps of PFAS levels in the throughout the US. So what are some of the better ways to treat water with a PFAS that has PFAS?
Well, these are, at least PFOS and PFOA are acids. Therefore, they have anions. Therefore, one of the methods that can be used to treatment is called anion exchange, which is feasible, expensive, but feasible. Another one is reverse osmosis, which is available, but also expensive. And the third one is granular carbon. Now, there's going to be some variability in different waters as to which one works best and which is going to be most costly. But all of them have the problem of once you have treated the water and produced this concentrate, which is now, much, much, much greater than what was in the original intake, what do you do with the concentrate? You can't send it to the sewage treatment plant. You must probably treat the concentrate. So you have to burn it off of the carbon or take the liquid concentrate and perhaps treat it by another process that will decompose, maybe high energy electrons, perhaps some kind of high energy process, short wavelength UV, maybe. Anyway, so that's an extra cost. The disposal, because it wouldn't make any sense to just put them back in the environment because they would just come back around, So not only is the treatment expensive, but the processing of the concentrated waste product from the treatment is also expensive.
So I would assume that concentrate would be a hazardous substance then,
Oh, sure.
Yeah, right. And as you mentioned earlier, American Water Works Association estimated the treatment costs would be much higher than what EPA suggested.
Which is normal. I mean, you have to understand when, people are people. So when you are regulating something, you want to optimize the benefits and minimize the costs. So by the fact that they came out with identical numbers indicates that they had a really hard time coming up with benefits and costs. So they basically said, well, because some of their earlier publications indicated benefits, but they withdrew back to equal.
Right. And so, Joe, you have been involved with the Safe Drinking Water Act since its inception with EPA. And I have worked in the past on arsenic issues, when it went from 50 parts per million to 10 parts per million, the maximum contaminant level. And, we talk about different sources. And I can remember asking my husband one evening what he was cooking for the kids. And he said, arsenic-laden chicken, because they give arsenic to chickens to make them more robust. But anyway, so oftentimes there's differences in these MCLs. For example, the US has an MCL for fluoride of 4 parts per million, and the World Health Organization has 1.5 MCL or guideline. So, sometimes the US is less stringent than the World Health Organization.
Yes.
And sometimes these regulations change. For example, they used to use different regulations for bacterial contamination of water, and then thought that it wasn't, it was too stringent maybe, and so then they relaxed it and just looking at E. coli itself and not total counts. So things change over time. So, but since you've been working with the Safe Drinking Water Act, if we're going to invest a lot of money in PFAS, it means that we will probably have less funding available for other issues related to water systems, possibly. And so, what do you think are important issues for drinking water systems in the US?
Well, first of all, there's no direct connection regarding World Health versus US EPA or the European Union. I mean, they all operate independently. World Health looks only at risk issues. They don't really deal with economic impact, which regulators have to deal with. Although World Health is concerned about costs, especially for low-income countries. So anyway, you have to assume that there will be differences, not only different people, but different environmental situations and different cost capabilities in different places. So Canada, US, EU, Australia, Japan tend to be pretty close together. Not identical, but sort of close together. The issues in drinking water these days are primarily groundwater contamination and a few others that I'll get into, but groundwater contamination, natural or otherwise, arsenic, natural groundwater contamination, and particularly in the western and the southwestern part of the United States, there are a number of locations where the natural geology has arsenic, sometimes pretty high, and it's very difficult and these tend to be small communities, and it's very difficult for them to put in the treatment to remove arsenic. We did a project in California, actually quite a few years ago, where we used decentralized point of use, where we installed a water treatment unit under the sink in every house in this community, and in the gas station, and in the post office, and in the restaurants. And it worked great. It cost half what it would have cost for them to put in central treatment. And in that case, by the way, it was an anti-exchange process. It was activated alumina. So different locations have different impacts. Now, as I understand it, EPA is in the process of re-examining the arsenic standard, and they might reduce it further. So that will create some issues. On the other hand, in terms of costs, a week or two ago, EPA put out its revised lead and copper rule. The estimated impact cost there is $45 billion to remove the remaining lead service lines around the country. And so, you've got a cumulative effect on water supplies. What usually happens is then they start coming to the Congress and they say, give federal money so we can do this. Now, to my mind, there are really three high risk issues, high concern issues that should be the primary ones. Number one is Legionella. And you say, well, Legionella grow in home plumbing. However, it's part of the drinking water supply system, of course. EPA doesn't really have legal authority on what happens inside your house and in your plumbing. However, Legionellosis is the only waterborne disease in the US and probably in the entire developed world that kills people. So you would think you want to do something about that, So I think that's a high priority. Now, EPA might not be able to regulate, but they can provide very specific informational guidance and recommendations as to what water suppliers and, in fact, buildings should do. One of the best solutions here, let's say for a hospital, is to have an additional disinfection system in the basement where the water pipe enters. Unfortunately, EPA makes it difficult for them to do that. EPA says, well, if you add disinfectant, you then become a public water system. And you then have to go through the certifications and the testing and all that other stuff, okay? So EPA could do things in the interest of reducing deaths and illnesses from legionellosis. Okay, that's one. Another one is small systems. We know small systems are just that. They're small. They don't have economies of scale. They don't have access to people with expertise. They can't afford to install, let alone run, sometimes sophisticated technologies. And so you need to have some creative approaches to dealing with small systems. And like the one I suggested, the decentralized point of use, which worked very well. And by the way, we worked very closely with the public in that community. It was about 400 people. They loved it. They said, this is great. The third one I think is very important is infrastructure, because remember, water probably gets very good treatment at the water plant, and then it runs into some pipes that are maybe 100 years old. And those pipes are not the same as they were 100 years ago. And the water that goes through them doesn't come out the same as when it entered, because there are mineral accumulations, there are bacterial accumulations, all sorts of things. So I think those are the three really top issues from a public health perspective for the future for water.
Right.
Legionellosis, small systems, infrastructure.
I'm quite aware of the small system issues. And you mentioned earlier that groundwater contamination is very widespread. So we did an analysis of non-compliance for community water systems in the US. And we found that one of the highest issues was geogenic contaminants from arsenic and radionuclides naturally occurring from the geology, and also of non-point source nitrates in these systems. So small systems is very challenging, and it's nice that you were able to do point of use treatment then in to develop a decentralized approach, because they cannot manage these systems or they cannot afford them oftentimes. And so we need to be more creative in how we develop solutions for these systems. So I'm really grateful for you for explaining PFAS and how the regulations have evolved and what they mean, and the variability among countries and, many different issues. And I'm sure, people will appreciate your background in these areas and your background with the EPA and Safe Drinking Water Act. So thank you so much. Our guest today was Joseph Cotruvo, and he is the president of Joseph Cotruvo and Associates.
And by the way, if anybody wants to call me and say, hey, what did you say? What did you mean? Happy to talk to them. And by the way, I teach a course called Drinking Water from A to Z. Is it safe to drink? And it's a very comprehensive, anything to do with drinking water. And it's it lets you know that drinking water is a lot more complicated than you think it is. It's not just turn on the tap and the water comes out. There's a whole history before and after. And so there's plenty to discuss on drinking water. Yes.
Thank you so much, Joe. I hope you have a good rest of your day.
You too. Thanks very much.
Okay.